There is a common misconception that the AI revolution is driven solely by mathematical breakthroughs occurring in a digital vacuum. In practice, even the most sophisticated algorithm is ineffective if it lacks a stable, high-capacity pipeline to deliver data. Jason Chuang's perspective on this problem began at National Tsinghua University, where he established a foundation in electrical engineering. At Purdue, his PhD research focused on theoretical machine learning, specifically techniques like bagging and boosting to increase classification accuracy. While these models performed well in controlled settings, academic theories often struggle when exposed to chaotic, unformatted data in live enterprise systems. To bridge that gap, Jason shifted his focus from the laboratory to the underlying infrastructure that allows internet-scale systems to function. This shift took him to Silicon Valley, working at companies like Composite Software and eBay during the peak of the big data era. San Jose provided a corporate environment where the scale of e-commerce data required a move away from theoretical modeling toward heavy-duty engineering. At eBay, the challenge involved moving terabytes of data across different platforms, specifically bridging the gap between Hadoop and Teradata systems. Processing millions of rows per second creates physical bottlenecks. When the flow hits gigabytes per second, even minor inefficiencies halt the entire system. Jason addressed this by developing a predictive model to identify these bottlenecks before they caused a failure. This approach was eventually codified as a U.S. patent for anomaly detection on Hadoop clusters. This experience demonstrated that data velocity is a physical constraint. Without a stable, high-throughput pipeline, an analytical model has nothing to analyze. Returning to Taiwan, Jason applied these lessons to the physical world, moving from cloud-based software to hardware integration as an entrepreneur. He founded AI for Quant, building a healthcare platform that used AIoT devices for early detection of heart disease in the elderly. This required a mastery of edge computing, executing models locally on small physical devices rather than relying on a remote server farm. Operating within these tight power limits earned his team the Best Technical Development Award from the Industrial Development Bureau. Building for the edge proves that an algorithm remains a theoretical exercise until it is optimized for the specific constraints of physical hardware. Currently, at Nexcom, the stakes of his work have moved into smart manufacturing and the security of operational technology. In these environments, security relies on zero-trust architecture, which treats every network request as a potential threat by default. Every request is assigned a dynamic trust score, fluctuating in real time based on user behavior, location, and connection health. If data suggests an anomaly, tools like OpenZiti isolate the request, protecting the broader network from a breach. For autonomous systems to exist in the real world, the security architecture must be as responsive as the AI it supports. Jason is currently building tools for agentic engineering, focusing on how autonomous systems interact with local environments and localized models. His open-source contributions, like the Ollama benchmark on GitHub, provide a standardized way to measure how efficiently these local models actually perform. He documents these findings on his Substack, Jason's AI Data Tools, where he analyzes the transition from traditional software development to the deployment of autonomous AI agents. This expertise is backed by certifications in NVIDIA's Agentic AI and Google Cloud's data engineering programs. Firm, Jason Chuang's path suggests that real-world AI capability depends on a command of the entire stack, balancing data flows, hardware limits, and the security layers that keep them running.